Greetings and welcome to the Chemistry 151 lecture for Chapter 2. I'm really glad to have you here. This should be a more exciting chapter after we got through Chapter 1's significant figures, scientific notation, stuff that's important, don't get me wrong, but not as exciting as this chapter. Really glad to have you here. Let's get into it. When it comes to chemistry, matter is of course super important, and matter is just anything that has mass. So if you can measure grams and stuff, that's going to be it. And all matter, as far as we know, has volume or space that it occupies. So matter is just anything with mass and space. A property is something that's like a characteristic that can be used to describe, for example, like one type of matter from the other. So for example, both liquid water and table salt are matter, but they're obviously different. One's a liquid, one's a solid. Those would be properties to distinguish the two. Now, in addition to things like the physical state, you can use size, something's bigger, smaller. Colors, obviously, would be cool. Temperature, those are also properties of matter. There's also things, though, like chemical composition, and that's what we'll get into, i.e. how many atoms a formula has and stuff like that. And the reactivity of chemistry is also important, too. So, for example, sodium chloride reacts in some ways that water doesn't, and vice versa. Chemical reactions, which we'll talk about later, too, is one way to talk more about how this all works out. A physical change is something that you can do on a substance that's reversible, yet it does give information as to what the stuff is. And this is actually pretty important. If you melt solid ice, liquid water ice, okay? If you melt it and it turns into liquid, that's an example of a physical change. You're changing the states. However, if we wanted to collect that liquid water and turn it back into a solid, that wouldn't be too hard. So that's an example of a change which is reversible. Sometimes some changes are much more difficult to reverse, and those we'll see are a different thing. But the physical changes and stuff are usually pretty reversible. Chemical changes, on the other hand, are generally irreversible, and this is where you actually have things going on at the chemical level. So, for example, if you take a piece of paper and you burn it, all right, well, paper burns, that's a chemical property, and you change the chemicals from the paper to the ash or whatever. But if you said, oh, I kind of want that piece of paper back, that might be kind of tough. Chemical changes usually are irreversible. There are some exceptions, but it's pretty tough. Some more common examples, rusting of iron. All right, iron turns into a new compound. We'll see it's an oxide compound with iron. That's hard to go back to the original iron. All right, it's not impossible, but it's very difficult, and that's kind of the idea. Matter exists in three main forms: solid, liquid, and gas, at least on the Earth. Let's keep it that way. But solid, liquid, and gas are the ones we're going to spend most of our time in chemistry talking about. Solids have definite shape and definite volume, all right? So you know right where it is, and you know approximately how much it takes up. Now, liquids have definite volume. So 30 milliliters, for example, of water is 30 milliliters. But if you have that 30 milliliters in a glass or as a pool on your kitchen table or something like that, still going to be 30 milliliters, but the change is going to definitely happen, all right? In the glass, it would be more compact, and on the tabletop, it would be kind of flat and stuff. So liquids will change their shape as they change their containers. Gases, on the other hand, have neither definite volume or shape. They just kind of go for whatever's around them. Harder to contain. You need to contain them, or else they kind of break free. In the lower right-hand corner are some of the names associated with the different transformations of matter, and we'll talk about those more in a little bit. Temperature is one way that you can change a state from one to the other, and water is, of course, the classic example. So water, it's easy to go from ice water, which is solid water, to liquid water, and you can turn liquid water into gaseous water or steam. That's when you boil something. Those are all changes of state, and if you look there carefully, going from liquid, gas, let me start at the solid, going from solid to liquid, that's an example of melting. And going from liquid to gas, that would be evaporating. And you can go the opposite direction. So for example, gases to liquids, that's called condensation. Liquid to freeze, like if you wanted to freeze that water we talked about earlier, that would of course be freezing. However, there are two other ones that happen for certain compounds more often than water. You can go straight from a solid to a gas using what's called sublimation. Dry ice, which is carbon dioxide as a solid, is an example of this. If you've ever been to a party and the Halloween juice or whatever, just say no, kids, but Prophet back on. If you ever been to a party and the liquid, the punch, whatever, is kind of fuming, a lot of times they put a piece of dry ice in. Dry ice is just carbon dioxide coming off. And if you take that gas and you make it into a solid again, you have what's called a deposition. Those aren't as common as the first ones we talked about, but they do happen. Here's a picture showing the solid, liquid, and gaseous states of matter, all right? And again, ice, very definite shape, very definite volume. Liquid water, all right, has a definite volume, but a variable shape. So if we pour that beaker of water on the table, it's gonna go all over the place. It'll be very flat instead of compact. And then finally, the steam. And by the way, the steam is this part up here and not the liquid part down there. But anyway, maybe the bubbles, all right, I'll cast that over. But anyway, steam, the gas water, has both variable volume and variable shape. They kind of expand out to go for crazy. In Chem 221, we're going to talk about what's called the kinetic molecular theory, or KMT, of matter. And that's really what we're talking about here. It's the theory used to describe the differences and similarities between the phases of matter, but that's more for a different course. Pure substances are important to chemists. If you're going to make something, you want to start with things that are pure. If you don't start with things that are pure, you usually won't be able to make what you're trying to make in the first place. Lots of examples of this around us. Sugar, if you've ever bought it from a store, sugar, little crystalline kind of things, that's a pure compound. And of course, if you go to the sink and get good water, that would be a pure substance as well. All right, so chemists are really interested in having pure substances. In the real world, elements and compounds can both be pure, and both sugar and water are examples of compounds. We'll talk more about that later. A mixture is when you have a variable amount of one species in the other, and there's lots of examples of that. If I told all of you to make me a sugar-water solution or sugar-water mixture, some of you would add a little bit of sugar to a lot of water, and some of you would add a lot of sugar to water. So the amount of sugar in there will vary, and that's exactly what a mixture is. And this is important too, because the sweetness of the water will be affected by how much sugar you put in, and of course how much water you put in. So knowing about the mixtures is important. Mixtures can be both heterogeneous and homogeneous. Heterogeneous means you have multiple phases. So for example, if you go walking in the woods and you come across a creek, you see rocks in the creek, that would be, in my opinion, a heterogeneous mixture. All right, because you have rocks, solid phase, and water, liquid water, in a liquid phase. They don't look alike, so you can totally tell they're different. You can also have two types of rocks in the same thing. Oil and water would be another example. All those kind of things. Now, a homogeneous mixture, though, is tricky. So the sugar water we quote-unquote made earlier, that would be an example of a homogeneous mixture, because probably you'd be able to stir it. The sugar would dissolve into the water, and it would look, if you will, just like water, or more correctly, it would look like a single phase. So homogeneous solutions are difficult to know if they're pure or not until you do some tests on it. Sugar water, definitely a homogeneous mixture, like we talked about, salt water, and there's lots of examples of this in chemistry. Sand is another example of a heterogeneous mixture. If you look at sand carefully, there's lots of types of rocks almost all the time. It's not just one kind. So visually, if you can see differences and stuff, that's a good way to see it's heterogeneous. Of course, some things would be under our eyes, but generally that's a pretty good idea. Earlier I mentioned how elements and compounds are the only pure substances, so let's talk about those. Elements are kind of like the building blocks of nature, all right? And they really are, as far as chemists are concerned anyway, the smallest pieces that make up everything that we know around us. Some elements are things you've heard of before. So for example, hydrogen and oxygen and nitrogen, those are all examples of elements, all right? And there's a whole bunch of them and stuff. We'll see. Compounds, which can also be pure, but compounds are definitely in combinations of elements that are well known, all right? But the thing about a compound is that you can break a compound down into other elements or sometimes into smaller compounds. But elements you can't break up. Elements are going to be there and they're stuck with you. Water is a compound, like we talked about earlier, and if you break water down, which is possible, especially with electricity, you will end up with hydrogen and oxygen. So in this case, water, the compound, can be broken down into the elements hydrogen and oxygen. And again, sometimes compounds go into compounds, sometimes compounds go into elements, and sometimes they go into mixtures. But compounds will break down. You can't really break down elements. Here's just a kind of a graphic. The top one there is, again, sugar water. And sugar water, if you undergo a physical change, i.e. add heat and evaporate the water is what I would do, you'd end up with pure sugar, because the sugar doesn't melt or anything like that easily. And water. The water can be evaporated, blah, blah, blah. On the other hand, if you break down water, which again is possible and stuff, water will break down through a chemical change into hydrogen and oxygen. You'd have to add electricity. It's not easy to go back to water unless you do it right. So this is just an example of what happens. So again, a lot of times you can break these things down into smaller substances, which is kind of cool. Here's an example, kind of an overview of how the things are. You start off with just good old matter, all right? And the first one is, are the properties and the composition constant? And if the answer is no, you've got a mixture. So for example, seawater is a good example of a mixture. If you go take seawater close to the sand, to the beach, then it will be different than if you take seawater, say, really deep in the Pacific Ocean or something like that. Those seawater is a mixture. If the composition is constant, then you're going to have a pure substance, and you can see how you can turn mixtures by physical changes into substances and back and forth, blah, blah, blah. Now, this is the important part though. If it's a pure substance, it's either going to be a compound, which is on the left, or an element. All right. And the way to tell is, can you break that substance down into smaller pieces? All right. Compounds you can break down to smaller pieces. But elements, though, you can't break down into smaller pieces easily. You'd have to use nuclear chemistry. It's basically not possible. But you can use chemical change to go from one to the other. So let's test ourselves. Let's see if we can figure out if these substances, which are kind of silly, but hopefully you get the idea, do you think that they are pure substance? Do you think they're compounds? Do you think they're elements? And let's think about it. So pizza. All right, I like pizza a lot, I'll confess. But anyway, pizza, right, duh, you look at it, there's crust, there's cheese, or if you're vegan, fake cheese, or vegetables, or whatever, all right, put over whatever you want on it. Pizza is definitely a mixture, right? There's no question. And every pizza is different, right? So you go to pizza place A, and that's going to be different than pizza place B, et cetera, et cetera. Now, Coca-Cola, gonna have a Coca-Cola with your pizza if you want, whatever. That's a mixture too, all right? You're going to have variable amounts of sugar, you're going to have variable amounts of carbonation, different types of sweeteners inside them. There's classic Coke and regular Coke, whatever. That's going to be a mixture too and stuff. So water, though, as we talked about earlier, water is an example of a compound. Water is made of hydrogen and oxygen, and you can break that down like we talked about into the elements. Silicon is actually one of the elements. Silicon is a major component of the Earth's crust, and silicon can be made into compounds, but if it's pure silicon, it's actually going to be an element. Iron is also an element. Iron's one of the building blocks of a lot of things around us, and we'll talk a lot about what that can do. But if you leave that iron out in the water for a long time, it's going to make rust, which is essentially an iron oxide. That's actually a compound. Rust is actually iron 3 oxide, and we'll talk about where that name comes from in a future lecture, but it is a compound, so you could break rust down into iron and oxygen if you wanted to. The elements are all found on the periodic table, and I say that because periodic table is, of course, hyper cool to chemists. This down here is a small version of the periodic table. There's about 118 elements known right now, which is totally cool. Now, all of those elements, only about 90 of them exist naturally. A lot of them are radioactive. They have to be made in the lab, or they just have super short times that they're going to be around. So really, on the Earth, there's maybe 90. Actually, that might even be too high. But anyway, not all of them you can go down to Fred Meyer's and buy. Okay, some of them have to be made in very special circumstances, and they don't last long. Some of them are really familiar to you, I'm sure. So like iron, tin, carbon, oxygen, hydrogen, sulfur, mercury, thallium. I don't know which ones you've heard before, but a lot of them are pretty relevant to our life. On the other hand, there's a lot of them that you may or may not have heard before. So niobium, rhodium, thulium, californium, and a whole bunch of other ones. We'll talk about those, of course, as we go through the case. But all the elements are listed on the periodic table. And these, again, are the building blocks of everything. So you look around yourself right now, wherever you are, you look around and everything you see is made up of atoms, all right? So in my room here that I'm looking at a window, and I'm looking at some papers, and I'm looking at some pictures on the wall, all made up of elements, all of them. Some of them are made into compounds, but it's kind of cool to think about it. It's kind of like Legos. When you have individual Legos, they're not that sometimes very exciting, but you can make just anything from them. You can make, huge buildings and R2-D2s, and who knows what they make with Legos, but you're building more complex things from those small Legos. When you're talking about an element, it's really a drag to write out hydrogen all the time, or, tellurium, or whatever element you're talking about. So chemists use a symbol system to quickly tell each other which one it is. And all of the element symbols are 1 or 2 letters. And the first letter always is capitalized. The second one, if it's there, will be a lowercase. And that's really important, all right? Don't try and use all lowercase. And if you're a person that writes in all caps, make sure that second one is a pretty small all caps, because that will drive chemists crazy. I'll try and be cool with you, I really will, but try to make it as lowercase if you can. Some of the symbols make sense to us in America, all right? H for hydrogen, that doesn't sound too bad. O for oxygen, N for nitrogen, or stuff like that. But some of them are a little confusing to us. So, for example, one of the most common ones is sodium. Sodium is Na. And you'd think, what? It's not SO or something? Well, this is a historical field, right? Chemistry's been around for a while. So Na is the symbol for sodium. It comes from natrium, and you can read more about that if you're interested through online sources and stuff like that. All these elements, like we talked about, are not equally abundant on the Earth, all right? So only about 90 or so of them are actually on the Earth in somewhat good quantities. But of all of the elements on the Earth, oxygen and silicon take up about 75%. So there's not as much gold, carbon, hydrogen, stuff like that. Oxygen and silicon really dominate the Earth's composition big time. We need what's called a chemical formula, which is a way that you can combine different elements together to show compounds. And in the formula, you're going to need some way to show if you have more than one atom of an element, and we'll see how this all works out pretty soon. Water's formula is H2O. And I want you to notice that nomenclature right there. There is a subscript 2, all right, and that's going to be really important. This tells the chemist that water has 2 hydrogens. So the subscript on the right refers to the element on the left, 2 hydrogens and 1 oxygen. And notice that there's not an H2O1, all right? If there's only one, that's omitted. So H2O would be 2 hydrogens and 1 oxygen. Every formula for every compound can be described similarly, and here's just some examples. So there's water, H2O. CH4 is methane. Methane is the active ingredient in natural gas. So if your house uses natural gas for heat or cooking, you're using CH4. Anyway, it's 1 carbon and 4 hydrogens. That next species is a type of a sugar, all right? And that sugar has 12 carbons, 22 hydrogens, and 11 oxygens. So any formula like that can be broken down. You can figure out how many atoms there are, et cetera, et cetera. So knowing the formula is really important for chemists, as you can probably see. On the periodic table, there are some important divisions which we need to talk about. This is an older periodic table, and I say that because if you look in the lower right, some of these elements down here are missing. And I just want you to be aware that in the real world, a lot of times periodic tables are shown that are not quite up to speed, and that's totally normal. The good news is that those lower right ones are super reactive. They don't last a long time, so it's not a big deal, honestly, if they're not there, but still, it's kind of sad. But anyway, back to the regular scheduled programming. On the periodic table, you're going to have metals, you're going to have non-metals, and there's also a few of these metalloids. And so if you look at the periodic table there, yellow apparently is the color for metals, and most of the periodic table is yellow. So that means that most of the periodic table is made up of metals. But the non-metals, which are the little blue elements kind of over here in the upper right-hand corner, and also don't forget hydrogen, which is usually considered a non-metal, those are also really important elements, all right? So on the periodic table, metals on the left, non-metals in the little tiny corner on the right, plus hydrogen. And if you look carefully, there's a purple line of elements going down the middle. It starts with B, which is boron, goes to Si, silicon, Ge, germanium, As, arsenic, etc., etc. Those are called metalloids, and metalloids are kind of a combination of properties, metals, and non-metals. And we'll see more about what this means later. Sometimes, for example, silicon can act like a metal, and sometimes it acts like a non-metal. So the metalloids are just ones that are kind of halfway, kind of stuck in limbo between metals and non-metals. We'll talk more about what all this means later, but I do want you to hear the terms non-metals and metals. That's going to be really important to us. Non-metals upper right-hand corner, and the metals are basically everything else on the periodic table except for hydrogen, and we'll see why that is in a later course. So again, just to reiterate, metals and stuff are always in the upper left-hand corner. And if you look at that little picture, the lower left one there, that's metals. That shows all the metals. All the metals are essentially solids at room temperature, except for mercury. Mercury, which is also known as quicksilver, is a liquid metal at room temperature. And we'll talk about this more. Now, metals are metals because they love to conduct heat and they love to conduct electricity. All right. And that's a real powerful thing about metals. Metals are also malleable, which means you can bend them, and they do give up their electrons to nonmetals, and we'll definitely be talking about that here later. Now, the nonmetals, which are basically the upper right-hand corner plus hydrogen, all right, their phases are all over the place. There's a lot of gases, all right, but there's also some solids. Bromine is a liquid, all right, so the two liquids at room temperature are bromine and mercury. The nonmetals like to absorb the electrons from metals, all right, so a lot of times the nonmetals will end up with extra electrons. We'll see what that means in a future lecture as well. Metalloids are that thin strip down the middle, which just means sometimes they act like metals and sometimes they act like non-metals. They're a lot of times used in semiconductors, which are what computers and stuff use, because they're pretty good about transferring electrons from one to the other, which is kind of cool. So let's test ourselves on these. Are these metals, metalloids, or nonmetals? And this is a good time to get used to the periodic table. Now, I'm showing the one here from the previous slide, which is fine. I really like the one that I'll recommend in other sources. It's the one we'll use in Chem 151, but try and have one next to you. If you're new to the periodic table, having an alphabetical list of the elements can be really helpful too. And you can find all these things online if you you can't find them, you let me know. So lithium, Li, is the first one, and Li is right there in the upper left-hand corner. That's a metal. It's called a main group metal, and we'll talk about that later. For right now, though, notice how there's 1A, 2A, and some metals here under 3A. Those are usually what they call main group metals, and we'll talk about that in a future lecture, like I said. Now, Au is gold, and it's hard sometimes to see where gold is. Gold is number 79 right there, and you got it. It's in the yellow, so of course it's going to be a metal. Gold is called a transition metal. All of the metals are in one of these B groups right here, and so gold is called a transition metal, and we'll see what that means more in a later way. Silicon is one of the purple ones, so that's a metalloid. Silicon can act both like a metal and a non-metal. Selenium, which is number 34. Selenium is a non-metal, all right, so no problem. And chlorine, up to the right of selenium, that's a non-metal as well. Chlorine is called a halogen. Group 7A is one of the more important non-metal categories. That whole up and down kind of category there that starts with F and goes to Cl, Br, I, etc. Those are halogens, and we'll see that's important. And then finally, the last one, Ne, is neon, and neon is also a nonmetal. That whole group, which starts with helium and goes neon, and then argon, I kind of covered up there, krypton, etc., those are all nonmetals, and they're officially noble gases, and we'll talk about those more later too. John Dalton kind of brought a lot of the ideas of alchemy and earlier scientists together, and he created some chemical assumptions that some people think actually started chemistry, and that's kind of cool, and we should talk about those here. Most of these ideas are pretty good at making up the current theory of atoms and how they work. Dalton thought, hey, I think that all matter is composed of atoms, all right? And I think he's right. Also, all matter has these little tiny parts in there. The atoms of one element differ from the atoms of all the other elements, and this is also true. So, for example, hydrogen is much different than helium, and carbon is much different than nitrogen. And we'll talk about why they're different later too, but he kind of figured this out, which was pretty cool. Chemical compounds have atoms in specific ratios, and this was actually important too. So water is H2O, we saw earlier, and water is something we all like to drink. We need to have so much per day. Hydrogen peroxide is H2O. It's one additional oxygen, and that one extra oxygen makes it just incredibly different. Like, you want to drink water, you don't want to drink hydrogen peroxide. It's an oxidizer, and it'll like rip your throat out and cause you to do bad things. Anyway, the water, it's a really cool compound, but in other circumstances, right? So water and H2O are compounds, and they have definitely specific ratios. And that's another thing. Water is always H2O. It's never HO2, it's never just HO, it certainly is not H2O2. You have to have specific ratios to make a compound. Chemical reactions change how the atoms are connected to each other, but the atoms themselves really don't change, and this is also pretty wild at first. So if you take hydrogen and oxygen and you make water, all right, you have the hydrogen and the oxygen separate, and then in water they're all combined. But you haven't destroyed or created any atoms, all right? You're just rearranging how they go together, and that's kind of a cool thing. So Dalton is kind of neat how he brought all that stuff together. Atoms are the smallest pieces of the elements. So if you have a bunch of gold and you cut it in half, you're still going to have gold. Cut that in half, still going to have gold. Cut. Finally, you're going to get down to the atom. And if you cut that atom, and it is possible, although it's not easy, if you do cut the atom, it's no longer going to be gold. It's going to be something else. So we consider atom to be the smallest part of any element. Molecules are the smallest pieces of compounds. So back to the water again, if you have a big thing of water and you take half of it, you're still going to have water. Half of that, half of that, half of that, still water. But you will finally get down to a molecule of water. And if you split that, it's going to break down into the individual atoms, or sometimes smaller molecules, but usually the atoms. So you're going to turn the molecule into atoms of an element. So you can break down molecules into atoms, but you can't break down atoms if you want to keep the atom. It'll be something else entirely, and it's not easy to do. Atoms have three pieces that make them different. So why is an atom of carbon, for example, different than an atom of nitrogen? And it comes down to the number of protons, neutrons, and electrons. And these three are called subatomic particles. Atoms are so small that we need to have a special mass scale, all right? Now, for example, if you take chemicals in a chemistry lab, usually you record them in grams, or if you're in an American supermarket, maybe you'd measure your apples, how many pounds of apples you have, something like that. In chemistry, we have to have our own scale too for this kind of stuff because it's so small. And what this thing is called, it's called the atomic mass unit scale, and it's really, really, really small. Now, a pound of anything is about 454 grams, roughly. An AMU, an atomic mass unit, 1.66 times 10 to the minus 24 grams. And that is really, really small. A lot of calculators can't even calculate numbers that are this small without going into significant figure or scientific notation because it's so freaking small. This AMU comes from the idea that if you have an exact carbon atom with 6 protons and 6 neutrons, it's going to be exactly 12 atomic mass units. And if you take that mass and divide it by 12, that's where this crazy number comes from. This isn't a number we're going to use a lot, but we will talk about AMU, and you can convert it, AMUs into grams, and then grams into pounds or whatever you want. But just realize, really, really small. A proton is about 1 AMU. So a proton is very, very small. That's number of grams. Oxygen is roughly 16 AMUs. So an oxygen atom is actually quite a bit bigger than an individual proton. So you can see here that we're already being able to distinguish some of the atoms from each other by their masses, by their atomic mass units. In the lower right corner is a picture of what an atom looks like, quote unquote, according to the current theory. And why that's important is because it shows how the the little subatomic particles, they aren't just evenly distributed in the atom. In the actual middle of the atom is what they call the nucleus. And the nucleus holds the protons and the neutrons. So you can see the little red and little green little knobs right there. Those are supposedly the protons and neutrons. And the electrons kind of circle around the outside. This shimmering blue kind of stuff around the nucleus, that's the electron cloud. It's where the electrons hang out. So all the protons and neutrons are in the nucleus, and the electrons are around the outside. Now, the proton and neutrons in the nucleus take up a very, very, very small volume. This picture here, this animation, doesn't really do it justice. So just realize that that nucleus should be much, 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 much smaller than the actual electron cloud. And what this means, and why we're talking about it, is that most of the atom is empty, all right? Most of it is just empty space. There's not a lot of stuff in the atom, all right? Those electrons kind of shimmering, they don't do much. The nucleus is so small, pretty interesting. So most of the atom pretty empty. This is a little bit better picture as to what the atom is like in terms of scale. Now, I want you to see here, the atom is roughly 10 to the minus 10 meters in diameter. Now, if you think of a meter stick, this is like more than a billion times smaller than the meter stick. So whoopee-doo, really, really, that's, it's still very small. But if you look at the nucleus, nucleus, which is on the right side, 10 to the minus 15 meters. So that nucleus is hyper small compared to the size of the atom. So you could draw like an atom and have a small dot in the middle. That would be closer to what the nucleus looked like relative to the atom. The nucleus is really, really small. And the atom is small too, but compared to the atom itself, the nucleus is really small. You can see many orders of magnitude smaller.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Rutherford is one of my favorite scientists, and he was the one that created the modern idea of what exactly the atom's all about. And he shot a type of a radiation with a positive charge at gold. And he used gold not because he wanted to show off or have bling, but he used it because it can be made very, very thin, at least to our eyes. And he used like a photographic plate around it to kind of show what was all happening. In the gold itself, you have these little atoms, all right? And that's what those little circles show right here. And the little kind of like ball bearing looking things right there, those are what they call alpha particles, and we'll talk about those more in Chem 200. But alpha particles are just really small. They have a positive charge. But the thing is, oh, and then by the way, he had like a type of a piece of film that went all the way around the gold. All right, went kind of like that. So you can imagine that the alpha particles are coming on that arrow, and they went there. Now, what was really interesting is that most of the alpha particles went straight on through, and he detected them on this piece of film, and you could just see this kind of smudginess on the film, basically. But what surprised him is that some of the alpha particles went crazy, right? Some of them almost went back and went there. You can see this one was going back. So some of them started going really crazy. And he deduced that most of the atom is pretty empty, all right? We talked about that, 10 to the minus 10 versus 10 to the minus 15. Most of the atom is empty. However, so that's why if it was empty, most of the alpha particles just went through right away with no problem. But if they happen to get next to the nucleus, those positive charged alpha particles, they reflected and stuff, or they diffracted, and this is something that happens in physics, but in a punchline, positives and negatives kind of mess around with each other. So that's why you see once in a while, some of them coming back at the detector, some of them going up here, some of them going crazy. It's pretty cool, but he was able to find how the atom was structured. They call this the gold foil experiment. And again, the punchline here is that by doing this, he found that most of the atom is pretty empty, but there is this really small part inside, which he called the nucleus. It must have been positively charged because the positive alpha particles were freaking out when they went next to it, which positives and positives repel. We'll see that later. Pretty cool. So Rutherford is one of the scientists, and just about 100 years ago, too, he really helped to figure out what was happening on the level of the atoms. Speaking of those forces, we should talk about that a little bit more. In terms of electricity, all right, there's basically things that attract, which makes them come together, and there's things that make them repel, go away from each other. And in these kind of electricity conversations, you can have something positive and you can have something negative. And protons are positive and electrons are negative. So if you get a proton and an electron close to each other, they attract. So unlike charges will attract each other. All right. Positives attract negatives. Negatives attract positives. All right. And that's what really keeps the atom together. The negative electrons on the outside are kind of kept in balance by the positive nucleus. That's enough to kind of keep it together. On the other hand, if you happen to have like charges, then you have repulsion. All right. And this is what happened in the gold foil experiment. The alpha particles that Rutherford used were positive, the nucleus was positive, and that's what caused them to repel. They try and get away from each other. There's two types of repulsion that are important in chemistry. You can have electron-electron repulsion, so electrons come too close, they get away from each other. But also really important, protons tend to repel each other if they get too close. So protons will try to get away from other protons normally. The nucleus is able to hold lots of protons because, first of all, you do have some neutrons in the middle. Neutrons we're going to see are neutral, so they kind of keep the protons away. But there's also another type of force here. It's called the nuclear strong force. And we'll talk more about that in Chemistry 222. But the nuclear strong force also helps keep those protons next to each other. But anyway, for our conversation right here, like charges repel. So electrons and electrons get away from each other, protons and protons get away from each other, but opposites attract, so positives to negatives. Cool. When chemists talk about an element, we need to know how many protons, electrons, and neutrons are in the atoms. And the first of these kind of ways that chemists use to talk about it is through something called the atomic number. Atomic number usually gets the symbol Z, and atomic number represents the number of protons in an atom. And all elements are defined by the number of protons. So let's go think about that periodic table we talked about earlier. If you look up aluminum, aluminum has a number 13 on it, and that 13 is the atomic number. So that means that aluminum has 13 protons. Now, even more exciting, atoms are by default usually neutral, at least what we're talking about in this chapter, all right? And if they're neutral, that must mean they have equal number of protons and electrons. So if aluminum has 13 protons and it's a neutral aluminum, then the electrons will also equal 13. So this atomic number is pretty helpful when it comes to figuring out different information about the elements. We'll talk about atomic weight here coming up, so just hold on. Mass number is something else that's important to us. Mass number usually gets the symbol A. Mass number represents the total number of protons and neutrons in an atom. So, from this slide, what I want you to see, first of all, is that atomic number, which is given the symbol Z, that represents the number of protons. And on the periodic table, we're going to see that all the elements have the atomic number listed. Second thing, atoms are neutral if the protons and electrons are equal to each other. So if you have neutral aluminum, you're also going to have 13 electrons. Mass number is the third thing to know. Mass number is equal to protons plus neutrons, and it's connected to that atomic weight, the other piece on the periodic table, but we're going to talk a little bit more about that. It's not the mass number by itself. Isotopes are atoms with the same atomic number but a different mass number. All right, and this is a really important part, and you've probably heard of isotopes, so let's try and define here what they are. Hydrogen has three main and important isotopes, and each of these isotopes is common enough that it has its own name. The names are protium, deuterium, and tritium. And the reason why they're different is the number of neutrons. Now, isotopes all have the same number of protons. So all of these are hydrogen, and they all have one proton. So you can see protium has a proton, deuterium has a proton, tritium has a proton. They're all hydrogen. That's what that means. But the neutrons is changing. So for protium, there are no neutrons. So A, which is the mass number, protons plus neutrons, 1 plus 0, mass number 1. Deuterium, which by the way is often called heavy hydrogen, deuterium has 1 neutron. So 1 proton plus 1 neutron is where the mass number of 2 comes from. And tritium has 1 proton and 2 neutrons, so 1 proton plus 2 neutrons, mass number of 3. We're going to see how these isotopes can all have quite different properties, but if you know about them, you can do some really cool things with them. We need a way to represent isotopes easily, and this is an example right here of boron, and these are 2 ways that people will talk about boron. Now, just to remind everybody that Z, the atomic number, is the number of protons, and that really does define the element. So if you change the number of protons, you won't have the same element. Mass number is A, and that equals protons plus neutrons. And you can see that both of these borons over here have a 10 on them. The first one is boron-10, and the second one is a superscript in the left-hand corner 10 with a B by it. And if you look at the periodic table for boron, boron is number 5. So the 10 is the mass number, and the mass number can be really important. So let's talk about if you have a boron atom with 5 neutrons. So if it has 5 neutrons, boron is number 5 on the periodic table, so 5 protons. That means the mass number is 10 AMU. So in the ones we were looking at earlier then, boron-10, the 10 is the mass number, or that superscript there, that 10 is mass number. The ultimate way to write an isotope is like this. Lower left-hand number is the atomic number Z, the number of protons. Upper left-hand number is the mass number, that's protons plus neutrons, and then the symbol for the element goes right there. This one is that's my favorite way to write the isotopes, but you will see like boron-10 or 10B sometimes. And you might think it's weird that in the 10B that they don't have the lower left-hand corner atomic number. The reason for that is that in programs like Microsoft Word and Google Docs, it's not easy to have both a superscript and a subscript on the same area. So a lot of times it's just easier to have only one, I'll be totally honest. On the other hand, boron, the B there, that tells the hip chemist that you're going to have 5 protons, because you can look it up on the periodic table. And 5 protons will always be boron. So it's not technically needed, but it is still kind of nice if you can do it. Back to the hydrogen, stuff like that, there's actually quite a bit of differences when it comes to the 3 isotopes of hydrogens. So ice, water, all right, the ice floats. And so ice, solid water, will float on top, which is no problem. If you can get enough deuterium to make heavy water, which is a deuterium-based water, so it's instead of having regular hydrogen, it would have deuterium right there. Anyway, or right there, I'm sorry. Anyway, you can see the ice made from solid D2O, from hydrogen that's actually deuterium, it actually sinks. It's more dense than liquid water. And finally, if you had tritium, which is the other isotope of hydrogen with 2 neutrons and 1 proton, tritium is actually radioactive, and you don't want to have a lot of this around at any one time. Now, there's always some tritium around us all the time, and we'll talk about that more in a future course where we talk about nuclear chemistry. However, small amounts are around, and that's okay. Tritium would be difficult to make and those kind of things. So all those isotopes quite different from each other. So as an overview, all of the atoms on the periodic table will exhibit more than one isotope. And here's an example of boron. Boron is mostly boron-10 and boron-11. And again, the difference between them is not the number of protons, because boron anything is going to have 5 protons. The difference comes from the mass number. So it doesn't have the number of neutrons explicitly. However, because boron has 5 protons, and 10 is the mass number, 10 minus 5 gives you the 5 neutrons there. For boron 11, you'd go 11, the mass number, minus the protons on the periodic table, 6 neutrons. So boron 11 would be like heavy boron compared to boron 10, I guess. That atomic weight, that other piece on the periodic table, is the most important part for chemists, and we'll see how this works out pretty soon. But anyway, that atomic weight is actually just the average mass of all the elements' atoms in a large sample. And it's all the one that includes all the naturally occurring isotopes of the atom. And that's really cool. So if you take all of the borons that are known, all right, you're not really going to have a boron 10 or a boron 11, it's going to be somewhere in between. For aluminum, this 26.9815, that's an average of all the isotopes of aluminum. Atomic number and atomic weight are displayed in the periodic table, but the mass number, the protons plus neutrons, is not, all right? And there's ways to make predictions, but just realize there's not really a mass number on the periodic table, and we'll talk about how this works out here pretty soon. Atomic weight is the average, and I'd like to use an example of boron to see how this comes around. Now, when people have studied boron on the Earth, they find that about 20% is boron 10 and about 80% is boron 11. So it would be nice to know what the average mass of boron is. What's really interesting is that if you've done things with statistics before, you can do this. So boron 10 is about 10 AMU, and boron 11 AMU. And when you're doing these kind of averages, you take the decimal version, so 20% becomes 0.20, or you divide by 100. 80% becomes 0.80. If you take the times the amount that it appears times its mass and add it with the other ones, that's how you get the average. So boron 10 is about 20%, or 0.20 of the time, and you add that to boron 11, which is about 80%, or 0.80 at the time. And this number, 10.811, that's the atomic weight of boron. And if you look on your periodic table, which hopefully you have next to you, the mass is something like 10.81 or 10.811. That's how they got this number. Boron 11, about 80%, boron 10, about 20%. And probably to make the version on your periodic table, they used better numbers than we are using here. Like they used more sig figs and stuff like that. But this is how those numbers come around, and that's kind of cool. Lithium is basically made of two isotopes. There's lithium-6, which is about 7.5%, and lithium-7, which is about 92.5%. And if you wanted to find the atomic weight of lithium, again, what you would do is you would just go to the periodic table. All right, there's no like surprises or anything like that. You would just look up and stuff what exactly it is. Lithium is about 6.941, so that would be the mass of the lithium. That would be the atomic mass of it. Silicon is another one. Silicon has 3 main isotopes, and you can see it's 92, 4.67, and 3.10. So if you look at the periodic table, the atomic weight of silicon in my periodic table is 28.0855, and you may have more or less sig figs, it doesn't matter, but that's how you find the atomic weight. Now, I would like to point out though, for example, in this number we just had for silicon, 28.0 whatever, notice how silicon 28 was the largest abundance. So usually the number that goes right there is very close to the isotope with the highest abundance. And this worked up on the previous example with lithium too. Lithium 7 was 92.5%, and the atomic weight was 6.941. So the answer, the atomic weight answer, is usually closest to the highest percentage abundance, which is of the isotopes, which is kind of cool. Here's nitrogen, two main isotopes, nitrogen 14 and nitrogen 15. And we have exact masses to lots of sig figs, and we also have their abundance. And notice, first of all, how almost all the percentage is locked up in nitrogen 14. So what that means, our average atomic mass should be pretty close to 14. All right, so keep that in the back of your mind. However, we can figure out explicitly what it is using these numbers. We take the decimal version of the percentage and multiply it by those individual masses, and you add it to the other one, same kind of process. So what that looks like, again, using the decimal version, that would be 0.996299 for that one, and 0.3701 becomes 0.003701. Multiply them by the isotope mass. 14.0068 is the AMUs, the average mass of a nitrogen. And that's kind of cool. So that's how they figure out all these different numbers. The first equation was on the last slide. Here's the X, here's the Y, the masses of the individual isotopes, and the average mass altogether. Now, the second line is new. Instead of using Y, we're using 1 minus X like we saw on the last slide. And now we have one equation with only one unknown X. To break up this 1 minus X, we use what's called the distributive property. 1 times 70.9249 is just that number. And minus X times that 70 number, minus 70.9249. So now we have two X terms. We can combine those two together. So go 68.9257 minus 70.9249. And that number, which will be negative, will be the number of X's. We can also combine the numbers on the other side. If we subtract 70.9249 from both sides, those will cancel out. We'll have another negative number on the left-hand side, and we'll be good to go. So if you do this, and I encourage you to try the math here, make sure that you've got it all figured out, you're going to end up with an X of 0.6012. And remembering that these are the decimal versions of these percentages, that means 60.12%. And that's the abundance of the gallium-69. We can go back and find the Y equals 1 minus X. So 1 minus 0.6012, you end up with 0.3988, and that of course would be 39.88% abundance for the gallium-71. So this is kind of a cool technique. It only works when you have two isotopes and you don't know their percentages. If you have three, you've got to go back to the drawing board. But with two of them, this works really well. Make sure you know how to do it. It's kind of a cool little technique to be able to master. Antimony is another element on the periodic table. It's number 51. And antimony has two main isotopes. Antimony 121, about 57.20% abundant, and antimony 123, which is about 42.80% abundance. Now, the average atomic mass of antimony, 121.7. It's about halfway between 123 and 121, more or less. And the question is, will you ever have one atom of antimony at 121.760 AMU? And the answer is a resounding no. You're not ever going to have one atom of that average mass. Average means you're taking different pieces and putting them together to find the thing. What this means, if you look back at these two parts up here, 57.20% of the time, you're going to have an antimony 121. So imagine you've got a big bag, all right, and about 57 out of 100 times, you're going to have an antimony 121 pulled out, if we could pull atoms out. On the other hand, the other isotope, 42.80%, that means that roughly 43 of the 100 times that I pull out antimony atoms, it'll have this antimony 123 with a mass of 122.9042. But we're never going to have one atom with that number. That's a statistically generated number. And sometimes in the United States, they talk about how the average family has 2.5 kids. And there's no family, all right, with like a half kid. That's morbid and gross and too weird to think about even for me. You're going to have families with 2 kids and families with 3 kids and families with 1 kid and families with 4 kids and 0 kids and 5 kids, etc., etc., etc. So 121.7 is like the 2.5 kids. You're never going to have a family with half a kid. You're never going to have, that's so weird. Sorry, it makes me think about it. Anyway, you're never going to have a family with half a kid. Definitely, you're never going to have antimony with a mass of an antimony atom with 121.760 AMUs. That's a statistically generated number. And you might think, wait a minute, why are we even dealing with this when you're not going to have individual atoms? Oh, my friend, we have such cool things to share with you here. We're going to see how that 121.760 allows us to do all kinds of cool things with antimony in a future section. So hang tight. Back to the periodic table, metals on the left, nonmetals on the upper right, with the exception of hydrogen, and again, those metalloids going down the middle. Lanthanides and actinides are 2 little parts. Notice there's a gap between 57 and 72, and the gap starts up right here. Lanthanides is this special strip at the top. Actinides is this special strip at the bottom. There's a gap right there. All these in the middle here, again, are the transition metals and stuff. So those are something we talked about earlier. Main groups on the periodic table are usually referred to with A's. So you can see there's a 1A, 2A, and the right-hand side, 3A is there, 4A, all the way through 8A. Main group metals and nonmetals are usually those regions right there. The transition metals, lanthanides, and actinides are kind of their own group. You'll also see that there's 2 numbering systems. So like there's a 1A and a 2A on the left, and there's also a 1 and a 2, and then the 3 goes down there. That's a different form of the periodic table. I call it the international version of the periodic table, and there's some cool uses for it. But in our class here at Mountain Community College, you want to make sure you're using a periodic table with 1A, 2A on the left, 3A above boron on the right, 4A, 5A, etc. I call that the American version of the periodic table. That's my unofficial name for it. That's not probably very cool. But anyway, it is really useful. But the other way does have uses too, and I can see why they do it. But we're going to use the 1A, 2A on the left, 3A through 8A on the right, and be good to go. Mendeleev was the first one to think about how this all worked out. Mendeleev was a real interesting person. His picture is in the lower right-hand corner there. Elements are arranged by increasing atomic number, all right? So hydrogen with atomic number 1, all right, is in the upper left, and helium with number 2 in the upper right, and then lithium, which is the next biggest one, right under hydrogen, etc., etc. On the periodic table, they have periods and they have groups, all right? And they're both important. Groups a little bit more important probably than periods, but that's important to see. So the periods go left to right, and the groups go up and down on the periodic table. And I'll show you better examples than my sloppy handwriting can do here in a second. I would argue that groups are more important than periods because groups have similar chemical properties. So all of the things in group 1A, which does include hydrogen, and we'll see why in a later lecture why that is, all of those 1A things like to, for example, lose 1 electron. Now, hydrogen's not a metal, but the other ones are, and those metals are very similar in how they react. And this works for the right side for the nonmetals as well. Here's a better picture showing groups and periods. This is group 2A. It's starting with beryllium and going down to radium. Group 2A is called the alkaline earths. I'll talk about that later. This is a period. This is the 4th period. It starts with potassium and goes all the way over to krypton. Periods have uses too. It's a different kind of a use, and we'll see that in a future lecture how this all works out. But just realize groups go up and down, periods go left and right. The first period, by the way, number 1, has just hydrogen and helium in it. But when you get down to the later periods, especially the ones down here with the lanthanides and actinides, oh my, there's a lot of elements in the periods. Some of the periods, or some of the groups, have very specific and important names. And these four names, I kind of want you to know. We already talked about just a second ago, alkaline earth metals are group 2A, and right next door are alkali metals, which is group 1A. So all the group 1A metals are alkali metals, and all the group 2A metals are alkaline earth metals. Sorry they sound so much alike. I didn't make the rules. I'm just the messenger. What are you going to do? Now, on the far right side of the periodic table, the halogens are group 7A, and that's chlorine, fluorine, bromine, iodine, stuff like that. Those are super important. And finally, group 8A, you've got the noble gases, and those are also kind of cool for different reasons. Transition metals or transition elements in the middle. These blue columns right here do have names, but they're not as common. You don't have to worry about it. I will use them later if you're curious, and then who isn't? But anyway, if they're not names you have to know. But please know alkali metals, alkaline earth metals, halogens, and noble gases.
The main engine of the NASA space shuttle is fueled by the elements oxygen and hydrogen. A huge amount of energy is required to lift the shuttle into orbit. When mixed and ignited, the fuels produce water and a large quantity of energy.
Hydrogen is the first of the elements, but it's by no means the least useful. And hydrogen, as you can see, is able to allow major spacecraft and stuff to get into Earth's orbit, or even beyond, using nothing more than it combining with oxygen to make water, which is really cool. Hydrogen is kind of unique. It can be somewhat metallic because it is in a more metallic side of the periodic table that we talked about earlier, but it's also a non-metal, so it has some very interesting properties, which are due to it honestly being small, but also having a lot of potential within it. Led Zeppelin, fans of the world unite, woohoo! Which of course I like. Led Zeppelin's first album has a picture of what's called the Hindenburg crash. That was right before World War II started. One of the big Zeppelin airplanes burned up. Hydrogen was used as the source for the balloons, and it caught on fire through ways which are still considered somewhat mysterious, and it's spectacular. There's a lot of history behind it. This is a picture of metallic hydrogen, and after I made a little thing there, this is the metallic hydrogen right there, sorry. Metallic hydrogen was predicted to exist in the core of Jupiter and places like that where pressures were really intense. And metallic hydrogen is true hydrogen acting like a metal, which is really neat. And a German group discovered this and took these pictures in January of 2017. So this is a pretty cool thing in my world, and we'll talk more about that in the 200 level. The group 1A elements are called the alkali metals, and they're generally very soft, like you can cut them with a knife. This is sodium. They do react, though, very violently with water. And, oh man, you want to make sure, for example, in this picture with the knife, you'd want to make sure that knife was very dry, because, man, they go crazy with water. Sodium, potassium, lithium are the main three. There's also cesium, different kind of things like that you'll see. We'll talk about these more in the 200 level too.
When magnesium metal burns, the product of the reaction has a greater mass than that of the original magnesium. John Dalton's atomic theory successfully explained this seemingly strange result.
John Dalton, who we talked about earlier, and another scientist named Lavoisier were both really critical in figuring out what was happening on the atomic level. Like, are there these small little pieces? And this magnesium to magnesium oxide reaction is such an example. In the little video there, they took pure magnesium and combined it with oxygen in a quite dramatic effect there, as you can see, to make magnesium oxide. And the mass of the ash weighed more than the mass of the metal they started with, and they rationalized it combined with oxygen, stuff like that. Pretty cool thing. Group 2A alkaline earth metals are very useful. Of course, magnesium, calcium is used a lot in our bodies, but the other ones are really important too. Barium has medical uses, but of course it's always also really cool in fireworks. It's got kind of a green color when it burns. Strontium, its same family, is also a firework thing. It's kind of a red color. So they're pretty neat, kind of neat elements. Group 3A, which is not a common name, nothing you have to know. The official name is icosagens, and that's boron, aluminum, gallium, indium, and thallium. And aluminum is very, very abundant in the Earth's crust. Now, silicon is more abundant, but silicon is a metalloid, so aluminum is considered the most abundant. Gallium's kind of fun. Gallium will melt in your hand, and so sometimes people will do jokes like giving people a spoon of gallium, and they'll put it in like tea or coffee and it melts and they think it's kind of funny. Anyway, whatever. Boron is very useful and stuff like that. Notice the name in the lower right corner, twisted metals. I will use this more in future lectures. Group 3A has some very different properties, and they're never kind of like happy. So I call them twisted because they're always trying to get to happiness and they're kept from it. But look, that's just my name. It's very informal and don't worry about it. Group 4A is super important because of carbon. Our bodies are really dependent on carbon and the kind of things it does. And carbon is also diamond and all kinds of things. But silicon is important too. Silicon's really important for geology. Germanium, tin, and lead have lots of uses for them as well. Of course, lead was used for plumbing. That's where the plumbing comes from, which was plumium, which is lead and stuff like that. Lots of cool things. Crystallogens is their official name. I think I'm saying it right. Maybe I'm not. When it comes to Group 5A's fancy name is pnictogens, and that's another weird name and nothing you have to worry about. Now, this is an interesting group because definitely the first three and arguably antimony are nonmetals. All right, antimony is more of a metalloid, but nitrogen and phosphorus, so important in the creation of life and fertilizers and stuff like that, really, really important. Bismuth, on the other hand, is a true metal, and it's a really cool metal. If you've ever seen a thing of bismuth, it's got this wild kind of refraction pattern, looks like rainbows on it and stuff like that. It's really, really neat. So bismuth is quite a bit different from its neighbors above it, which is kind of interesting. Ammonia is a really important part of nitrogen's family. Ammonia is also used in fertilizers and for a whole bunch of different things. You will save yourself some pain if you just know / memorize / make yourself a tattoo. No, don't do that. Seriously, make sure you know that ammonia is NH3 because water and ammonia have a lot of similar properties. And everybody knows water because, of course, we drink it. You wouldn't want to drink ammonia, but ammonia does have a lot of really cool uses. So know somewhere in the back of your mind that ammonia is NH3. An interesting story on phosphorus. You know, chemistry didn't just happen overnight. It was around the time of John Dalton we saw. But before that, there were lots of alchemists, and they were always trying to make things gold-like. They thought that was the purest form and stuff like that. Well, this guy, Brandt, in 1669, looked at his maybe urine. Let's hope it's, I don't know. Anyway, I digress. Anyway, he tried to get gold out of urine because he thought, oh, it's golden. It must be pure. Well, no, the color came from many other things. But anyway, along the way, he did discover phosphorus, and phosphorus is super important and super cool. So anyway, I don't want you to think that all chemist jobs involve analyzing urine. Oh, that's kind of gross to even think about. But anyway, you can see that this dude was into, and it was kind of cool. And also shows that sometimes you just have to explore things, and you'll find really neat things along the way. It may not be what you thought, but it still will be cool. Group 6A, which has the fancy name chalcogens, but you don't have to know that either. Oxygen, of course, so important for life. Sulfur and selenium, also important. Sulfuric acid, of course, is a big industrial chemical, sulfur in volcanoes. Tellurium, polonium, not as used and stuff, but also pretty interesting stuff. So it's a cool thing. We'll do a lot, of course, with oxygen and sulfur and a little bit with selenium.
The reaction of sodium and chlorine is a vigorous one. We use sand to protect the flask from excessive heat. Then, we fill the flask with chlorine gas. Next, we add sodium. And then a few drops of water to activate the reaction. The reaction produces sodium chloride.
In this reaction, they took a stoppered Erlenmeyer flask, which is what that flask is called, and they put a little sand in the bottom just to give it some energy so it wouldn't crack the glass. Then they gave a lot of chlorine gas into the flask so it kind of stayed inside, and they added a piece of sodium, which was activated, if you will, with a few drops of water. And oh my goodness, in the formation of sodium chloride, which is table salt, you can see the amount of energy which is released. It's just incredible. And that's a pretty fantastic thing about science. But anyway, this is an example of the power of the halogens, which is group 7A. And this is a real important group of nonmetals we're going to see a lot. The first four especially, fluorine, which is F, chlorine, which we're seeing here, bromine, and iodine, all have really interesting uses when it comes to the real world. And we'll see examples of this later on. But the halogens is a name I'd like you to know. It's something that's going to pop up a lot, so keep that in the back of your mind. The noble gases are kind of fun too. Of course, they are all gases, all the way from helium at the beginning to radioactive radon at the very end. The interesting thing to me about noble gases is they thought really you couldn't do much with them. You couldn't make any compounds. They were able to use them for like ballooning. This is an example of an old scale balloon. However, in the early 60s, they were able to figure out a way to make compounds with some of the noble gases. And this is one of my favorite right there. It's a xenon compound. The xenon has an oxygen, that's the red atom, and the fluorines are these green ones right here. So this is the xenon in the middle, all right? This was one of the first compounds made with a noble gas, and everybody used to call this group the inert gases, which means they don't react. They do react. They've made compounds now with xenon and krypton, but I am yet to be convinced that they've made compounds with the other ones, but xenon and krypton have been made. Neon, of course, is used for neon lights, for signs and stuff, so if you've ever seen those at night, thank the noble gases, but don't call them inert gases anymore because obviously they've made some compounds. The transition metals are a group, again, in the middle of the periodic table, and a lot of times those are placed in the same family as the lanthanides and actinides. Transition metals are really cool. This is one of the areas that I studied a lot in graduate school, and transition metals just have beautiful colors. You can do like so much with them. They're really, really exciting. Transition metals have properties which make them different from the main group metals, and we'll talk about more about what that means. Iron 3 oxide is rust. We talked about iron rusting earlier. That's what it is. It's actually technically an iron compound with oxygen. We'll talk about what that Roman numeral means, but in almost all of the transition metals, you will need a Roman numeral to express it. Okay, that's it for Chapter 2. I hope you enjoyed this kind of quick overview of some of the properties of chemistry. Hopefully you've got a better idea about how the periodic table is organized. Some of the names are kind of familiar to you. If you have questions on this or anything else, please email me, let me know. I'm happy to help you and talk about these ideas in more detail. Have a wonderful day.